Hello, welcome to our deep learning lecture. Today we will discuss on how to apply backpropagation to recurrent neural networks. The resulting algorithm is called backpropagation through time. So at various points of the lecture, we've touched things like vanishing gradients, exploding gradients, numerical stability, and these are quite important things when thinking about applying backpropagation to recurrent neural networks. So in principle, backpropagation through time is nothing else than applying the chain rule to efficiently compute the gradients, as we always did, to recurrent neural networks, just that the computational graph is derived by rolling out the steps over time. So the forward pass is pretty much straightforward for recurrent neural networks. Backpropagation through time requires us to expand the current neural network one time step at a time to obtain the dependencies between model variables on the one side and our parameters. Then we apply the chain rule to derive our backpropagation algorithm to compute and store the gradients. However, since sequences can be rather long, this means that also the dependencies in our computations can be quite lengthy, or the dependencies also between the beginning of the sequence and the end of the sequence. Let's look at an example. So for a sequence of 1000 characters, the first symbol could potentially have significant influence on the symbol of position 1000. Computationally, this becomes infeasible. So it just takes too long and requires too much memory to do the computation for our backpropagation algorithm. So the computations required to, in the forward pass, storing all the intermediate variables, and then in the backward pass, to compute our gradients. It also requires over 1000 matrix vector products before we arrive at this gradient that we want to compute. Let's look at a little bit a simplified mathematical model of a recurrent neural network to illustrate the problem. In this neural network, we take inputs x at time point little t. We have hiddens, so a hidden state, hidden variable at time point t, and this is computed as a function of, well, our inputs, and of course, because we have recurrence, the hidden state at t minus 1, together with some weight parameters. Given this hidden state at time point t, the output is computed as a function g of our hidden state alone, and some parameter weights of this output layer. So again, xt denotes the input, ht the hidden state, and ot the output. And in this recurrent neural network, we basically get a chain of values from 1 through capital T of these xt, ht, and ot triplets. And these triplets depend on each other via a recursive computation that we have here in F. So that means that we need to loop through the triplets xt, ht, and ot one step at a time. Once we have computed this, we can compute our objective function, which compares our computed outputs ot with some ground truth labels yt. So objective function is capital L, takes as an input our recurrent neural network inputs, our labels, and the weights of the neural network. Then it uses the neural network, so our functions f and o, to compute all the outputs given our inputs and our weights. So one output at a time, and then the next one depending on the last hidden state. And then once it has computed all of these outputs, it can look at loss function little l that compares each output to the correct label and applies a loss. And then we average over all of these little l's. So next is that we want to use backpropagation to compute the gradients with respect to all our parameter weights. So we want to differentiate the objective function L with respect to WH and WO. So first, the differential of the loss with respect to WH. Remember, our loss is a sum, so capital L is the sum over all our little l's, thus the derivative also becomes a sum. So basically we have the sum over the derivatives of little l with respect to WH. Now in order to compute this derivative, we need to apply the chain rule twice, namely this term here, dl of yt and ot, dwh becomes dl of yt ot with respect to ot times the derivative of g of ht and wo with respect to dht. This we can take the differential of dht with respect to wh. Now the last term is where it becomes complicated. Now if we compute the derivative of this last term, dht, dwh, using the chain rule, we get the following recursion. So dht, dwh equals df of xt and ht minus 1 and the weights wh with respect to dwh plus df xt ht minus 1 wh with respect to ht minus 1, and then we need to use the chain rule, so we get dht minus 1 dwh. So the term dht dwh requires us to compute dht minus 1 dwh, which in turn requires to compute the term dht minus 2 dwh, and so on and so forth. So we have a recursion. Now let's simplify this term a little bit. So first, assume we have three sequences, AT, BT, and CT, and these satisfy that A0 equals 0, and that AT is computed from BT plus CT times AT minus 1. So this is exactly the type of recursion that we had for the computation of our derivative of HT. And now for T1, 2, and so on, we can see that for T larger or equal to 1, that AT is equal to the sum of BT, here, plus the sum from index I equals 1 to little t minus 1, the product of index j that starts at little I plus 1 through t, cj times bi. And now this formula we can just use to compute our derivative of ht. By plugging in the terms at equals derivative of ht with respect to wh, the term that we want to compute, bt equals the derivative of f of xt, ht minus 1, wh with respect to wh, and ct the derivative of f xt, ht minus 1, wh with respect to ht minus 1. So we can see that the gradient that we want to compute, so the gradient ht with respect to wh, satisfies this at equals bt plus ct times at minus 1 recursion. So we can plug in the same formula as before. So the derivative of ht with respect to wh is equal to the derivative of f at ht minus 1 with respect to wh plus the sum index I equals 1 through t minus 1 of the product index j equals I plus 1 through little t of the derivative of f at hj minus 1 with respect to hj minus 1 times the derivative of f at hi minus 1 with respect to wh. And while we can use the chain rule to compute this derivative recursively, this chain can get extremely long whenever t is of significant size. Now, as we already said, this leads to a computationally very hard, expensive problem in terms of storage, in terms of time. So it's somewhat infeasible for larger t's. And it can also be numerically unstable. So what can we do? Well, I mean, the first thing that we can do is we can just naively compute it. So we compute the full sum. Now the problem is that this is very slow and the gradients can blow up, since already small changes in the initial conditions can have a potentially large effect on the outcome. So changes in h0, our initial state, can affect, ht for a larger t a lot. So this is somehow similar to a butterfly effect, where small changes in the initial conditions can have disproportionate changes in the outcome. And this is actually quite undesirable, because if you think about what our goal here is to do, well, we want a model that can generalize well. So it also means that it needs to be somehow robust. It needs to be a so-called robust estimator. And now if we have an estimator where small changes in this initial state can have huge effects, this is the opposite of robust. So even though computing the full sum is exact, it's actually not really what we want. So we could actually say that we're actually writing down the wrong model. So this strategy is actually never used in practice, or almost never used, at least for larger t's. An obvious alternative strategy is, if you want to compute the derivative of ht, that we take the gradient, propagate a little bit along the time, and then truncate after a fixed number tau steps. So this leads to an approximation of the true gradient. So remember the true gradient we get from the full computation. Approximation, where we are terminating the sum over the derivative of ht with respect to w at the term derivative of ht minus tau, so this fixed number of steps with respect to w. Now in practice this actually works quite well, even though it's an approximation. This algorithm is commonly referred to as truncated backpropagation through time. One of the consequences of truncation is that the model will focus primarily on short-term influences. Because we are truncating our gradient computation, we don't let information flow from the initial states to current time, but only through a fixed number of steps. In practice, this is actually often desirable, since it will bias, so regularize our estimate towards simpler and more stable models. The problem of truncating after fixed steps is that it's an approximation where we actually get a biased estimate of the gradient. So that means, well, it's obviously not exact. However, it's not even in expectation exact. So an unbiased gradient would be one where, well, each individual estimate of the gradient may not be correct. However, if we average over many of these, we would get the correct gradient back. And there's a trick. We can introduce randomization in a special way to actually get such an unbiased estimate of the gradient, where what we want to compute is the gradient of ht, the hidden state of time t, with respect to our weights. And in randomized truncation, we replace this by a random variable. So it's something that is stochastic. But this random variable actually has the correct expected value. So the expected value of this random variable is exactly equal to the gradient of ht. But it still computes a truncated sequence. How can we get such a unbiased estimate of this ht with a truncated sequence? Well, it's achieved by using a sequence of these xi t's, where for 0 smaller than a parameter alpha, which is again upper bounded by 1, so it's a number that is smaller or equal to 1, the expectation of xi t equals 1. We have a probability that xi t equals 0, and this happens with a probability of 1 minus alpha. And we have a probability that xi t equals 1 divided by alpha, so that it takes a value that is larger than 1, with a probability equals to alpha. So you can think of, you flip a coin, with a probability of alpha, you accept the value 1 divided by alpha, and if that event doesn't happen, so the alternative event is that you set the variable to 0. If you look at the expected value of this, so we have two different values. We sum over the two values. In the one case, we have the probability of xi t equals 0 times the actual value, namely that it takes 0, plus the probability of xi t equals alpha inverse times the value, which is alpha inverse. Now, these probabilities are 1 minus alpha times 0 plus alpha times alpha inverse. The whole thing is the expected value of xi t, the multiplication here. So we have 0 here, and this becomes 1. So this expected value equals 1. And now we use this random variable to replace the gradient with zt. So instead of computing the gradient of ht with respect to w, we compute zt, which is given by the gradient of f of xt ht minus 1 w plus xt times the gradient of f xt ht minus 1 w times the gradient of ht minus 1 with respect to w. So what have we just done? Well, we multiplied this random variable xt to the right side of the sum in ht. So if we didn't have this xt here, this would be the same thing as writing down our prior equation for the gradient of ht with respect to w. But this xt can, with a probability of 1 minus alpha, be 0, in which case this whole term, it becomes 0. And with a probability of alpha, it becomes 1 divided by alpha, so a value larger than 1. So what this means is that with a probability of 1 minus alpha, we are truncating the gradient computation, because this whole term becomes 0. And with the probability of alpha, we go one step further in the gradient computation and then again flip get another one of these XCTs for the next step. So because then we enter the recursion, one step, but we upweight it because we're multiplying by 1 divided by alpha, which yields a number that is larger or equal to 1. And similarly to the expectation of XCT being equal to 1, the expectation of this ZT, so of this randomly truncated gradient, is also the actual gradient. So the exact computation of this actual gradient would require us to compute recursively the whole sequence. We randomize it by randomly truncating it, and if we're not truncating, we upweight the samples a little bit. If we're truncating it, we are subtracting something essentially because we're losing this whole sum. However, when we are going further to we upweight these, so these two operations in expectation, once we average over many of these, cancel each other. Thus, we get something that is unbiased, that has the same expected value. So each sample is different, but in expectation they're the same. So this leads to a weighted sum of sequences that have varying length, where long sequences are rare, but appropriately overweighted. Unfortunately, this is on the one side quite appealing in theory, however, it does not work that much better than the simple truncation. And that could have a number of reasons. One is, well, the effect of an observation after a number of these backpropagation steps into the past is already quite sufficient to capture the dependence in practice. Remember, there's also always noise in the sequence. So dependencies get also a little bit lost through the noise in the sequence. Second, the increased variance that you get by introducing this upweighting counteracts a little bit the fact that the gradient is unbiased, or that it's more accurate in expectation. Third, well, even though we want to write out these models that allow propagation of information from the beginning to the end of the sequence, in most cases we actually want models that only have a short range of interaction. Hence, backpropagation through time has a slight regularizing effect if we truncated it, and that is desirable. Now let's look at these three cases to perform backpropagation through time in this example, where we compute a sequence model on the time machine by H.G. Well. On the first line we see randomized truncation, which partitions the text into segments of varying length, because we are computing these sequences that truncate randomly. Regular truncated backpropagation through time always goes back tau steps. So this yields sequences that all have the same length. And third, full backpropagation through time is the case where we allow information flow from the first element all the way to the last element. So this would yield exact computation. However, it leads to something that is computationally infeasible because we get these large recursive expressions. Finally, let's look at an example recurrent neural network and do backpropagation through time on it. So here we have the computational graph of a recurrent neural network that only has linear latent variables. So linear means that we take our inputs xt, we multiply them with a weight matrix W, hx. It's recurrent, so also we take the hidden variable at the last time step, t-1, and multiply them also again linearly with a weight matrix WHH. So we take these two linear expressions, sum them up, and this yields our current hidden variable ht. And given our hidden variable ht, we can compute the output at time t as the product of a weight matrix WQH with this current hidden variable HT. So in this example, we see a case where we have 3 time points, so capital T equals 3. And we see how the computational graph in this case is rolled out. Yeah? So we have our recurrence, the computation, we do one step at a time. That gives us all our computational dependencies. So in the beginning, we have our input x1 and our initial hidden state h0. Using the corresponding weights, we can combine these to linearly compute the first hidden state. Now this is combined with the next input to compute the next hidden state. At the same time, we also use this hidden state to compute the first output. Now this output is then added to our computation of L, which is given as the sum over our little l. So it's 1, L equals 1 divided by T, sum T equals 1 through capital T, little l, O, T, Y, T, right? So we're comparing at each time point the predicted output, which is computed as a function of H1, to the correct label Y1. Similarly, we would do that for given H2, we compute O2 and then compare it to Y2. And finally, in the third step, we compute from the third input x3 and the second hidden state, the third hidden state H3. There we can compute the third output and compare it again with y through 3 to compute the final term of our loss function. So we have this linear recurrent neural network. In principle, you could do the same thing also with nonlinearities. The computational graph would look the same. But for the sake of simplicity, we keep it all linear. We have 3 weight matrices, WHX, which has dimensionality equal to the number of dimensions of the hidden variable times the number of the dimensions of the input. We have the weight matrix WHH, which has the dimensions equal to the number of hidden variables to the dimension of the number of hidden variables. And our third weight matrix WQH, which has as dimensions the dimensionality of the output times the dimensionality of the hidden variable. So little l OT YT is the loss at time step t, and our objective function is the sum over all these individual losses. Now, if we apply backpropagation through time to this, our goal is to compute the gradients with respect to all the weights. Well, the first step is that we start here and we compute the gradients with respect to these outputs here. So the gradient of L with respect to OT. Because our loss is just a sum over all the little l's that compare the teeth output to the teeth label, we also get this as basically the gradient of little l at time step t back divided by, well, t, because we're taking the average, so we have t, capital T total time steps. So we have the gradient of little l with respect to the teeth output for each of these time points. Next, we can calculate the gradient with respect to the weight QH, so the weight that is applied to the hidden variables. And this is given by, well, the sum, because we're basically having the sum over all these L's. So we now aggregate over all these capital T terms. So that's why we have a sum of the product. So this is applying the chain rule. So the prod of the gradient of L with respect to OT and the gradient of OT with respect to the weight matrix. And because our model is linear, so because OT is just a product of HT times WQH, the second gradient just becomes H transpose. So this term goes here, and here we have our HT transpose. So this is the general form for an arbitrary neural network with an arbitrary nonlinearity, but for the linear case we get the simplified term here. Next, we can compute at the final time step, capital T, the objective function L, which then depends on the hidden state HT, H capital T. It depends it only via O at the capital T. For that reason, we can easily compute the gradient delta L delta H transpose using the chain rule. So this becomes the product dl dot times dot dht. Again, because OT is computed as a linear function of H3, we get back the weights of this linear function as the gradient. For our simplified linear neural network. Now for any other time step with t smaller than capital T, the objective function depends on ht via ht plus 1 and ot. Now according to the chain rule, the derivative of LH with respect to ht at this time step little t, which is smaller than capital T, can be recurrently computed as the prod of dl dht plus 1 that it depends on times the derivative dht plus 1 with respect to ht plus the prod of dl dot and the derivative of ot with respect to ht. Now again, because these are linear neural networks, so the dependency of ht plus 1 on ht is linear, and thus this gradient becomes WHH transpose. This is this term here, and this is this term. Similarly, OT depends on H via the weight matrix QH, WQH transpose. So in our simplified linear neural network, we get the sum of these two matrix vector products. Even though our simple neural network only has 3 steps, let's, just for illustrative purposes, expand this term for an arbitrary large capital T. So recurrent computation for any time step little t, which is between 1 and capital T, gives, so the gradient of L with respect to h little t is the sum from index I equals t to capital T, the weight matrix WHH transpose to the power of capital T minus I times WQH transpose times the gradient of L with respect to O capital T plus T minus I. Now what we see is that we compute potentially extremely large powers of this weight matrix here. Now, if we look at the eigenvalues of this matrix, some of them may be smaller than 1, some may be larger than 1. If we multiply a matrix with itself, what will happen with the eigenvalues? Well, we're taking the product of the eigenvalues with themselves. You may remember that from linear algebra. If not, I tell you now. So what happens with an eigenvalue that is larger than 1 if you multiply it with itself? Well, it becomes a little bit bigger. What happens with an eigenvalue that is smaller than 1, if you multiply it with itself, it becomes smaller. And if you do take a large power, so you're basically multiplying these eigenvalues many times with itself, the ones that are larger than 1 diverge towards infinity, and the ones that are smaller than 1 go to 0. So they vanish. Thus, this gradient computation is numerically unstable, which manifests itself in the form of vanishing and exploding gradients. And one way to address this is to truncate the steps at computationally convenient size, as we discussed before. So finally, let's compute the gradients with respect to our two weight matrices WHX and WHH. The gradient of the loss with respect to WHX is the sum little t equals 1 through capital T, prod of the gradient of L with respect to HT with the gradient of HT with respect to WHX, because HT is computed as a linear function. It depends on our inputs xt transpose. And here, this is this gradient of TL dHT. Similarly, for the gradient of the weights of the hiddens, this is the sum from little t equals 1 through capital T, prod of dL dHT with dHT dWHH. Again, as HT is linearly computed via HH with the linear function of the hidden state at the last time point, HT minus 1, we get here, this gradient back, the vector HT minus 1 transpose, and this gradient here. Everywhere the quantity dL dHT is this key quantity that affects the numerical stability that we just have computed, which involves these recurrent computations, in this case matrix powers. So let's summarize. Backpropagation through time is just the application of backpropagation to sequence models with hidden state. However, due to computational reasons and for numerical stability, we need, for longer sequences, to truncate this sequence. We've also seen that high powers of matrices can lead to divergent and vanishing eigenvalues. In fact, if you make the power high enough, it's actually the largest eigenvalues that will dominate the computation. This manifests itself in the form of exploding or vanishing gradients, and for efficient computation, intermediate values can be cached, as we always do in backpropagation. So with this, I want to say thank you and see you next time. Bye bye.